I just want to say one or two things about the lab, although I mentioned it to the group that I had yesterday, but maybe the group that I have on a Monday might be a tiny bit confused, or maybe not. Let's see. So if I go over to the website, so this lab here notionally is the lab that you're finishing off this week. You do not need to submit that lab to me. This lab here is the one that you will work on next week, and you do need to submit that. I think I made Friday afternoon, late afternoon, the submission date for this lab. And again, it's a bit like the TypeScript lab submission. You'll just create a repo and upload to Moodle a simple little text file containing the URL of the GitHub repo. And you'll be pushing to that repo during this lab. Okay, that's that. So in terms of today's lecture, we're still on this topic of serverless. And so the slides I'm going to go through today are behind this card here. I've kept on adding slides to the set that are behind this card until I finish this topic, which will definitely be next week. So then we'll have covered all I want to cover in relation to serverless, and we move on to a different topic after the midterm break. So where I left off the last day was talking about DynamoDB. And maybe just to go back one or two steps. So we know it's a non-relational database. And one thing that was kind of unique about it, maybe not unique, but certainly unusual, was this idea here that the actual data, so in DynamoDB, you create tables, standalone tables. You don't create a database and then tables within that database. You just create tables. Of course, it's a serverless database system. But so you create a table. You could have more than one possibly, but the data in a table is actually spread out over a number of physical partitions. Each partition is managed by a separate computer. And that's the way it works. And why did the DynamoDB designers decide to take that approach? Well, it's really all got to do with performance and latency. If all of the data was housed in one physical, managed by one physical computer, then, for heavy traffic loads, heavy requests, but whether they be read or write operations, the performance is going to be impacted if it's all just focusing in on one partition, i.e. one computer that's managing the hard disk. So instead, they took this partitioned approach. So now, as we said the last day, now when a request comes into DynamoDB, whether that be a read or a write operation, one of the request is going to specify the partition key of the record, although we don't call them records, we call them items, but effectively they're records. It specifies the partition key of the record that it wants to operate on, whether that be a read or a write. And DynamoDB has an algorithm that it puts the partition key value through that algorithm, and the algorithm spits out the partition number associated with that item. And then it talks to that particular partition. So there's this idea that each record stroke item that's stored in a DynamoDB table has to have a partition key attribute. And if I go back to this slide, so when you're creating a DynamoDB table in your CDK code, fact, if I go forward one, that's the code there. All you've got to specify in the CDK code is what is the primary key for this table. You don't actually need to tell it about the other attributes of the items that are stored in the table. And that's because DynamoDB is schemaless. Schemaless means that really you can have items of different structure all within the one table. But you do have to declare what is the primary key for a table at the outset. And we talked then a little bit about primary key idea. So there's two possibilities. One is there is one attribute of the set of attributes associated with an item, which is unique for each item in a table. And if that's the case, then it's easy. The partition key and the primary key are one and the same thing. And just make sure that the well, it's implied really, I suppose, if it's unique for each item, if the particular attribute that you've chosen is unique for each item, then it has a diverse range of values, and that's good because that will allow DynamoDB to spread the items across the multiple partitions that I was talking about. However, option 2 is where, you know, there isn't a single attribute in the set of attributes associated with an item that is unique. That doesn't, you don't have that luxury, if you like. In that case, you've got to create what's called, or design what's called a composite or a compound key. And a compound key has two parts. You can't have compound key with more than two parts. Otherwise, if you're faced with that situation, then you've got to rethink your table design completely. But in this option 2, we're saying that there is a combination of two attributes associated with an item, which when those two attribute values are combined, they uniquely identify an item within a table. And of those two attributes, then you've got to choose one of them as being the partition key attribute and the other one as being what's called the sort key or hash key attribute. And again, the partition key one will be the one that has the more diverse range of values. And so the example I'm giving you here is, let's suppose we've got a table that stores the results for each user playing a game on some sort of online gaming platform. Okay, there are going to be more than one game that's supported by this platform, but there are a large number of users. So the user ID might be a suitable partition key, but because a user can play multiple games, multiple types of games, I suppose, let's say, then there's going to be more than one item in this table where the same user ID is going to appear. So user ID is not sufficient as a primary key for this table. We need a second attribute, and we've chosen the game ID as being the second attribute. So game ID is my sort key, user ID is my partition key, and the combination then is the primary key for this table. And you would express that in the CDK code. The partition key in this situation still has the same role as before. It's used by DynamoDB to determine where to put an item in the set of partitions associated with this table, and equally where to retrieve an item from. The sort key, so typically, yeah, sorry. So the set of items for a particular partition key value is referred to as an item collection, which I'm mentioning over here. So an item collection is a group of items that have the same partition key, but a different sort key. And because they have the same partition key, that means they're stored on the same physical partition, hardware partition. So they're kind of grouped. Okay, that's that. Now, I covered all of this stuff the last day, so I'm not going over that again. Other than maybe to say that the types of operations that you can carry out on a DynamoDB table are single item, query, or scan. The query ones are the ones that were kind of into single item or straightforward, you know, where you're trying to just add a record, update a record, delete a record item. I keep using the word record, but add, update, or delete an item in a table. And clearly, for single item operations, you have to specify the primary key of that item, whether that be a single value primary key or a composite primary key, doesn't really matter. Query operations only make sense in the context of a table that has a compound primary key. Doesn't make sense otherwise, okay? And for query operations, typically what you might be doing is requesting a collection of items that have the same partition key, but a range of values for the sort key. Yeah. So going back to our gaming application example, we want, let's say, all of the results for user 1, 2, 3, 4 for all of the games that they have played. Or maybe we are only interested in, if I go back to that table, maybe we're only interested in getting all of the items for user 1, 2, 3, 4 for any game that had a game ID of greater than 2000. Let's say the game IDs numbers have some sort of meaning in this context. So you can specify with the sort key part, you can specify the range of values that you're interested in retrieving from the database. Hence, that's why it's called a kind of a sort key. Or indeed, it's called a range key as well. So that's query operations. So here, yeah. There's no other type of request that you can make to DynamoDB. So it's a lot more restrictive than the SQL that you would be familiar with from relational databases. And so that's why when you are designing DynamoDB tables, you've got to think hard about your primary key, especially if it's a compound primary key. Scan operations, just for completeness, scan operations are effectively operations that would require DynamoDB to scan all of the partitions that make up our table. Clearly, scan operations are fairly inefficient, and you try and minimize the number of scan operations that an application needs to do, but they are available to you anyway. Now, this is really where I left off the last day. Local secondary indexes. And this only applies now to tables that have these compound or composite primary keys. It turns out that you can actually specify up to 5 secondary, what are called local secondary indices for a table. When you create a table that has a composite primary key, then we would call that table essentially the main index representation of the table, okay? A secondary index is essentially a complete copy of the table, but what's different in the secondary index is that while it has the same partition key, the sort key attribute can be a different one from the main index. So these local secondary indices, even though the name might suggest that it's just another index that's added to your table, a local secondary index is actually a complete copy of the table's data. So that means on any particular partition, there may be more than one copy of the table being stored on each of the partitions. Now you can instruct DynamoDB to not make a full copy of the table for these secondary indexes. You can define what's called a projection, which means that you only want certain attributes from the main index to be projected into the secondary index. And the existence of these secondary indexes, and I'll talk a little bit about them in a second, but the existence of a secondary index, and I said there can be up to 5, means that, let's say when we add a new record to a table, then obviously there's a copy of the record stored in the main index, but there's another copy stored in each of the secondary indexes. Okay, so that's a read can result in multiple writes to a partition. Right. So the bullet points are: it's an alternative secondary index associated with a table. That's what an LSI is. These LSIs are stored locally to the partition. They have to be, right? They're stored in the same partition that the main index is stored in. And okay, if you have multiple partitions, that means each partition will have secondary indices, but the secondary indices on each partition only relate to data on that partition. You can have up to 5 LSIs, as I said. So these things can grow, like obviously, you know, if each item in the table is a couple of megs, and you have some secondary, and there are a couple of you know, thousands of items in a table, then you have, you know, multiple copies of that data all being present on each of the partitions. So it grows quite quickly. Now there's an upper limit of, I think, 10 gigs per partition, that kind of idea. Again, this is all part of the design of DynamoDB that makes it quite different from any type of databases that you might have come across up to now. These local secondary indices, what they mean is that we can now query our database based on these local secondary indices. Going back to my gaming application, we only had one index defined. That means we could only query that gaming table based on a user ID and a game ID. Okay, but if we've got a secondary index, and the secondary index will only be possible if there is an alternative, if there's another attribute that's suitable as a sort key. But if we have a local secondary index, then it means we can do other types of queries as well based on that secondary index. And that means when you, from a coding point of view, when you write the code to carry out a query operation on the database, you have to indicate in the code which index should be used to execute this query. Should it be the main index or one of these local secondary indices? The attributes that you choose must have, okay, the attributes of the attributes of the alternative attribute that you're picking for the sort key has to be a scalar value. That kind of stands to reason. It has to either be a string or a number. The sort key always, and indeed the partition key, they always have to be either of a scalar type. They either have to be of type string or type number. There's a binary as well, but we don't care about that. If I just, let's see, if I fast forward to this, right? I took this straight out of the DynamoDB online documentation. So we've got a table here that, what are we told? It's a table of discussion threads for a social media platform, let's say, social media application. And here's my table, let's call it my primary index, or okay. So the partition key is the forum name. Again, they're just using the different AWS services as the forum names. That's okay. That's my partition key. My sort key is the subject. So it have to be strings in both cases here. And then there's also a last post date, which is just another attribute in this item. And let's say there are other items, there are other attributes as well. There's a reply count, and let's say there are more. So so this is my table, and this is what we would really call now the primary index representation of this table. But let's supposing there is a requirement to be able to query this table based on, give me all of the discussion threads for, let's say, forum S3 that occurred in 2016. Okay, I want to send a query to DynamoDB to retrieve those items for me. Okay, I want all of the threads for the S3 forum that occurred in 2015. Now, because the sort key is not dealing with date, the sort key is just based on subject, then that means I have to carry out a scan operation on this table in order to get that information. So the scan is going to have to read the entire table, and then I would look within my Lambda, I guess, I would have to go through all of the, well, I guess I could get all of the, sorry, let's rewind a little bit. I can actually get all of the S3 items, but then I'm going to have to process them myself to find the ones that relate to 2015. But I do have to bring all of the S3 items in, even though, strictly speaking, I know it's small numbers now, but I would only need these two. Okay, and this one is, well, let's say we picked 20, are they all 2015? They are, unfortunately. Let's say I want them for the month of January 2015. Let's broaden it out a little bit, or narrow it down a little bit. The point anyway is that because of the sort key that's associated with this table, queries based on forum name and date means that I have to actually bring in all of the items related to S3 and then process them locally myself. However, if I defined a local secondary index where I essentially kind of switch these two guys around, in other words, this is my local secondary index now, and I have a sort key based on date. That now means I can actually write a query which will say, give me all of the threads for the S3 forum whose date begins with the string 2015-01, or did we say February 02? And DynamoDB will send that request to each of the partitions, and the partitions will return the exact items that I'm interested in. You see, we want to minimize the amount of data that's being transmitted between the partitions back to the DynamoDB service, and then on to us. So we want to minimize the amount of traffic being sent between those three entities, if you like, the client, the DynamoDB service, and the actual partitions, which are remote from DynamoDB. So that's the benefit of these local secondary indices. And the local secondary indices that you define are really dictated by the types of queries that you think your application is going to need to be able to make. So you do have to make decisions on the types of queries that you are planning to run against your table. You have to decide those things up front, if you like, and they will dictate the local secondary indices that you add on to your table. But of course, all of this only works now for this particular example. This last post date as my choice of the sort key within this local secondary index, that only works if the combination of S3 and the date is unique. We're still back to that requirement that combination has to be unique. So strictly speaking, which stands to reason, I suppose, if we tag on the actual timestamp onto this is treated as a string, by the way. DynamoDB doesn't have the luxury of dealing with date types. So this is just a raw string as far as it's concerned, and it can only process it as a raw string. That's why I said we could query it on the basis of give me the S3 items, essentially that begin with the substring 2015-02 or whatever you were interested in. Okay, that's local secondary indices. And just to go back to here, is there any points I missed here? I haven't shown you in this week's lab, actually, as I think about it. Well, sorry, next week's lab, you will see how I define these local secondary indices in my CDK code, because I do have to declare them up front. They have to be part of the kind of infrastructure, if you like. And I've already made this point that each LSI is a separate physical representation of one logical table. I've kind of made that point already. One index is deemed the primary or main index, and the others then are called, hence they're called secondary indices. There's also this notion of, or this facility called global secondary indices. I'm not going to cover them, but they essentially allow an index to be cross partition, whereas these LSIs are within a partition. The GSIs are across the set of partitions that make up your table. Okay, the final point I will repeat is whether you want local secondary indices or not, that is determined by the types of queries that your application needs to make against the data in your table. If for this example here, the queries would only ever be give me all of the items for a particular forum where the subject contains or begins with a particular substring. If they are the only types of queries that were going to be executed against this particular table, then I don't need the local secondary index at all. However, if I do want to be able to make queries based on the dates associated with threads, then I do need a local secondary index. Or otherwise, I'm going to have to read in too many records from the database and process them myself within the Lambda based on looking at the date and filtering out those that are not relevant to me. But at that stage, all of the data has been shipped from the partition to DynamoDB over to my client or over to my Lambda. So all of that extra movement of data is something that we want to avoid for performance reasons. Let's see. Oh yeah, that's okay. Right. That's all I want to cover with DynamoDB. And I've already given you an insight to the fact that, you know, there's a lot more that I haven't covered, like these global secondary indices, but that's okay. We have enough to be reasonably productive with the service itself. I haven't well, I've shown you some, sorry, now I'm going back and forth, but I've shown you one or two examples of how you read and write to DynamoDB. There's plenty of examples in the lab. I talked through the structure of the code for reading, I think, the last day, which is, so I'm not going to go back over that again. But obviously, this is the code that would appear in the actual Lambda itself. But I talked about it the last day, and there are examples in this week's and next week's lab. So that should be enough for you. Right, I want to move on to yet another serverless service called API Gateway. And if you think about developing a serverless app, there, according to this screenshot, there are three kind of components to a serverless app. There is the actual functionality, if you like, or the logic. We now know that the Lambda service is one service, one serverless service that we can use for, that we can leverage to locate our logic or our functionality. We haven't looked at another one called Fargate, which is a container-based serverless service, but I'm going to stay away from that. Then there is the kind of the state management or the information management or data management side of your application. Well, we've just been talking about DynamoDB, although S3 also fits into that that aspect of a serverless app. RDS is there is a relational databases are obviously supported by the AWS platform. There is a database called Aurora, which is a serverless relational database service. But we're not going to look at that. And then there's the whole area of communications between the various let's say, components or parts that make up your serverless app. Now, today I want to look at one service that facilitates communication, and that's API Gateway. These two over here, SQS and SQS, they're very important as well, but I'm going to deal with those later on in the module. I'm not going to look at Kinesis at all. So where API Gateway fits in, and this really is kind of a reference back to what you would have done in the Web App Dev 2 module last year. API Gateway essentially allows us to create what we might call serverless REST APIs. So an API Gateway typically, although as we see, not uniquely, API Gateway typically sits in front of if you can imagine, I've got a whole bunch of Lambdas here, okay, that each provides some piece of functionality. And I want all of these Lambdas to be accessible to my client or invocable by my client. Well, one way I could do it is I could have each Lambda, give each Lambda its own unique URL. We know how to do that. But the problem with that is that, you know, all the URLs are completely unrelated. So it's not great, really. A nicer approach would be if we could route all of our requests to invoke a particular Lambda, route them all to one endpoint, if you like, and then that being the API Gateway, and then that takes care of routing it to the appropriate Lambda, taking the response back and sending it back to our client. This is a three-tier architecture because typically as well, there has to be a persistence layer, and we now know our persistence layer might be DynamoDB. So this is your classic three-tier serverless web API architecture when you're using AWS as your platform. And so we need to talk just a little bit about this API Gateway, but it's API Gateway is much more flexible than just being a front end for your, what I often refer to as your backend Lambdas. So first of all, we would say that API Gateway is a fully managed, and we know now that fully managed really is a byword for serverless. So there's no maintaining of a server involved here, although, you know, there are actual servers being used behind the scenes, as we know. It allows us to essentially kind of create REST APIs. We know what REST API endpoints, we know that language from last year's web app dev module. Some of the other points that I'm going to mention down here, we won't get to practice, but just to quickly go through them, I'm saying that the API Gateway also supports the WebSocket protocol. WebSocket protocol, as you might know, allows both push and pull communications. So it will allow your backend to push data out to your client without being requested from the client. So it's that kind of two-way bidirectional communication. So API Gateway can be configured to support WebSocket endpoints, essentially. You can have it can handle the versioning of your web API. You know, in real life, an organization that has a web API that is being used by clients, then, you know, presumably that web API grows over time and evolves, and there are different releases of the web API or different versions of it, but you still want to be able to make old versions available to clients that still want to use the old version of the web API. Well, all of that kind of versioning is built into the API Gateway, and you can configure to have multiple versions of a RESTful web API available to your clients. Again, we're not going to look at that. It supports different environments. Clearly, that's going to be important in production in a real world environment. You'd want to be able to support a dev environment, a test environment, a prod environment. The environments can actually be called anything you want them to be. They're not prescribed as dev, test, and prod. But so it supports that. So you can have essentially parallel incarnations of your web API running at the same time. It can handle, well, all the security is, all the security, it's not handled by the API Gateway itself, but it can dovetail with other services that provide authentication and authorization. In particular, there's a service called Cognito, which we will look at later on. So API and this Cognito service, they can, you can configure them to talk to one another for the purpose of providing authentication and authorization aspects to your web API, which you would have programmed last year, if you remember. You would have programmed all of that yourselves, but we can offload a lot of that to this Cognito service, which, again, as I said, we'll talk about later on. You can, if you want to, get API Gateway to generate API keys. Remember when we were using the TMDB service last year, in order to use the TMDB web API, essentially that's what it was. We had to apply for an API key. Well, the API Gateway supports this key generation aspect, and obviously then it checks for any requests that are being sent to it. It checks for the presence of an API key and the validity of the API key and all of that. We won't take that API key approach. We will take the more kind of traditional username, password authentication approach. It has support for Swagger and OpenAPI. You might remember Swagger was that web API specification language from last year. We won't get to look at that either. You can build in data transformation and validation. Like if I go back to here, sometimes, although not always, it's appropriate for data validation to go on here before it actually sends the data on to the Lambda. So that maybe there's some preliminary validation that can be carried out. And if the validation fails, then the API Gateway will take care of sending the response back rather than waiting for Lambda to do that. Just bear with me for 1 second. Just want to check one thing, please. I'm going to stop sharing my screen now just for a second. Okay, back with you again. Yeah, you can configure API gateway to do some preliminary validation of the data that might come in with requests. You can also get it to maybe transform the data into a form that's suitable for whatever is over here. And as I said a couple of times already, it doesn't have to be a Lambda that's over here. It could be something else. So that idea of data transformation is something that you can build into your API gateway. There is a feeling, though, that the API gateway shouldn't have too much functionality or logic built into it, because that's probably more appropriate for, a Lambda or some other logic component rather than hardwiring it into your API gateway. That's a fairly low level pointer. Anyway, it is possible. Maybe if we leave it at that. You can also get it to generate an appropriate STK for a web API, which is something we could have done last year, but we actually didn't. So like last year when we were talking to both TMDB and the web API that we developed ourselves, in our React code, if you can remember, we were actually hard coding the HTTP calls to the web API. It would be a lot nicer if we actually had a little SDK that, and it's inside in the SDK, that's where all of the hard coding of talking to, well, not so much hard coding, but that's where all the low level communication, HTTP level communication goes on, rather than in our source code. So you can actually get API Gateway to generate an appropriate SDK for a particular web API that you have developed using the API Gateway. It can do caching of responses, and it can support direct denial of service. Okay, so it's quite powerful, really. It has a lot of features in it, but for time restriction reasons, we're only going to look at a small subset of these. So you have your API gateway, and you've got something to sort of behind it, as I say, or to the right of it, based on my kind of diagrams. On the previous diagram, it was a Lambda we had behind it, or to the right of it. But as I've already said a number of times, any number of services could be linked to your API gateway. And so as part of the configuration of your API gateway instance, you have to specify what's called the integration type. What type of integration are you hooking the gateway up to? So there are 4 types of integrations. We will only use one, but just to go through the 4. So there is a kind of a default one called a mock integration, which really means that requests that come into the API gateway, it deals with them itself. It doesn't actually pass them on to any other service. Okay, and that might be suitable when you're starting up, you're building your API gateway, your REST kind of web API. Maybe you don't have the backend developed yet, so you can set up mock integration endpoints. The second type of integration is, unfortunately, now they're kind of called different things. If you read different documentation, there's no kind of consistent naming from them. So that's unfortunate. But anyway, I'm calling it here. It's the HTTP AWS integration type. Now, an example of that would be what I'm showing you down here, right? Where the backend is not a Lambda, it's some other service. For example, SQS might be a service. So the idea here is now we still got a RESTful front end here, but maybe there's, for let's say, post or put requests, the data accompanying those requests, they have to be transformed into an appropriate format before it can be forwarded on to the service that's going to deal with them. Okay. And if that is the case, if there is a requirement for that transformation, then the type of integration, the integration type that we need to configure our API gateway to use is this HTTP AWS integration. And so you have to somehow express the transformation that needs to be carried out by API Gateway. And so there's what are called mapping templates that you actually have to code up using a language called VTL, Velocity Templating Language. It's not a very nice language, to be quite honest. It's a declarative language, but so you have to write these mapping templates and then associate those mapping templates with your API Gateway instance and associate them with this particular integration type. And then API Gateway takes care of the rest, really. When requests come in, it applies the mapping templates to any data, any body accompanying the request, and it then just passes that transformed version of the body of the request onto, in this case, SQS or whatever other services over here. The third type of integration, which is the one that we will be using, is called AWS Proxy. And in AWS Proxy, it's nice. There's no transformation involved, so that's fortunate, because that transformation templating language, as I said, isn't really that developer friendly. So simply the requests that come in, and so if I go back to one or two slides to here, okay, this AWS Proxy is the appropriate integration type when it's a Lambda that's at the back end. And so your HTTP request comes in, and what the gateway does in this case is essentially it converts the HTTP request into converts the request into essentially a JSON structure. So you can imagine here we've just got JSON here now at the other side. If I can write properly, there's JSON. Okay, that's what's being sent over here. And if our Lambda, our Lambda likes JSON structures, it knows how to process those. So it doesn't have to deal with raw HTTP stuff. In this JSON would be the body of the request, but all of the HTTP headers, any query string parameters, all of that stuff is nicely packaged into this JSON structure. Now, admittedly, you do have to, in the Lambda, you do have to have an understanding of the structure of the JSON object, but at least it's JSON, and that's more easily processed than HTTP. So that's what happens if the integration type is this AWS Proxy integration type. Let's go forward again. So that's integration type number 3, and there is a fourth one called HTTP Proxy. And with HTTP Proxy, it's HTTP on the left and it's HTTP on the right. Okay, there's no conversion into a nice JSON format. A typical example of where this integration type would be suitable is if you had an application load balancer here. So that's a valid configuration to actually have an API gateway in front of the application load balancer. Application load balancers were kind of part of the architecture, kind of pre-REST web API era. So, but other than that, this type of integration takes HTTP and essentially kind of forwards on or proxies on the HTTP onto the backend service. API, the application load balancer likes HTTP, obviously. And there's no mapping templates or any of that involved in this integration type either. So it's quite easy to configure from a API gateway point of view. The other thing you have to do with API Gateway is to configure the CORS side of things. And I'm assuming people are familiar with CORS. Typically, the typical kind of use case for CORS, although it's not unique, is if you've got a web app front end and an API backend, essentially what you developed in the web app dev module last year. And that's kind of what I'm illustrating on this screenshot. I did say to you, I think at one stage, but you may have forgotten at the beginning of this lecture, you know, the React app that we developed last year, we could have actually hosted that on the S3 within an S3 bucket. You can configure an S3 bucket to be the host for a front-end web app. It doesn't have to be React, it can be any type of web app. And so if you imagine, I've got a React app that's being hosted within this S3 bucket, and let's supposing that's the URL for accessing that app. But this URL, sorry, but the React app in this case, it wants to talk to this web API over here that's being managed by API Gateway, but the domain name for the API is different from the domain name for the React app. Hence, you know, we have to configure the CORS configuration for this API Gateway to determine whether this particular React app from this particular domain can make requests to our API on the right or not. And as you know, the way CORS works is the client will send a kind of a pre-flight request to the gateway, asking it, you know, sort of telling it, this is who I am. Let's see, which way does it go? This is who I am, and this is who you are, kind of essentially. What kind of requests can I send to you? And here's the response back from the pre-flight request from my client. And it's kind of telling it what type of requests it can make to this particular web API. And then the React app actually, or our web app actually makes the request if it's allowed to do it or not. That's how CORS work, as you know. I'm sure CORS has been explained many times to you, but that's just a visual explanation of how CORS work. So the point from an API Gateway's perspective is we have to configure our API Gateway accordingly as to what kind of other domains are allowed to send requests to this domain. So let's say I have this objective of I want to create an API Gateway instance and configure it as a RESTful front end. And so I would write my CDK code, which I'll show you in a minute. And on executing that CDK code, then we would just simply go to the API Gateway service, and we would see evidence of the gateway instance that has been created for us. And if we clicked on that, and this would be coming from this is all generated by the CDK code now, of course. If we clicked on that, then it brings us to a screenshot that I'm showing you down here. And if you select the resources on the left here, essentially what you see here in the middle is a kind of a visual representation of the design of your web API. And so for this particular kind of trivial one, if you like, I just boost it up a little bit. So this particular web API I have, it has a to-dos path, and the to-dos path supports get and post method calls. Within the to-dos path, there is a subpath where we can actually specify a to-do ID. So to get at this path, it would be /todos/ to-do ID. And this endpoint or resource within this overall API, it only supports GET requests. And if you click on any one of these, what the management console will show you on the right is it'll show you some details associated with that particular endpoint. And so, for example, it's telling us that the integration type is, well, it's calling it Lambda proxy here. Lambda proxy was the third one. I think I called it Lambda proxy. In fact, no, I called it AWS proxy in my set of slides. And as I said to you, it's called different things by different people. But so Lambda proxy is the one where it takes the HTTP request and it converts the request into a JSON representation and forwards that on. And in this case, it's forwarding it on to, well, it has to be to a Lambda because that's the nature of this type of integration. It's also telling us here something else. It's telling us that there is no authentication checking required with requests to this particular endpoint. So anybody can send a post request to this web API, as it turns out. Later on, we'll see where it will be require authorization. That's when we bring in the Cognito service, as I mentioned. Other than that, is there anything else that we need to look at? So it's giving us a nice kind of visual, representation of the design of our RESTful web API that we can confirm. Eventually, we have to get the code. So this is the CDK code for all of this, and just take it from the top. If we pick it up, okay, let's assume I do need a Lambda, so we're not really interested in the Lambda at this stage behind the scenes, but there is a Lambda. And here's how I create my API gateway instance. And in particular, I want it to be a RESTful API. There is another type of configuration that you can have for your API instance, which is called the HTTP API. It's not as powerful as a REST API configuration. That's the downside. The upside of that HTTP API configuration, though, is that it's actually cheaper from a cost point of view to use, but we're not concerned with cost in this case. So I'm taking the more functional one, which is the REST API. So this creates anyway an API instance for me, and it's going to support all aspects of the REST architecture. Again, same old story. I have to connect this API gateway instance to a stack, and I'm attaching it to the current stack. That's just the name I want to give it. And then the rest is some configuration. Here we have the CORS configuration. I haven't been, it's pretty open-ended in this case, but I do have to think this is a mandatory part of this configuration object that you're passing to this class. The other properties, description, okay. Developer options. Remember I talked about the fact that you can have multiple environments associated with a particular web API, a dev environment, test, prod, and whatever you want to call it. So I've decided this is going to be part of my dev environment. And that's about it. So that just creates, if you like, this just creates an API gateway instance, but I haven't configured it yet. And by configure, I mean, I haven't told it about all of this stuff down here. What are the various endpoints associated with this API gateway instance? And that's where this code comes in. So I need to add a resource in the language of API gateway, add a resource or add an endpoint to my gateway. And I'm adding this endpoint, I'm adding it to the root of my RESTful web API. In other words, I'm adding it to, this is the root here. I'm adding it to that. And what do I need to tell it? I need to just give it, well, this is actually the path name for this endpoint. So it'll be the /todos. So that string is going to be part of the URL, if you like, to the endpoint. And that's it for now. Here I'm specifying what methods are associated with this endpoint. In other words, I'm adding a method to this particular endpoint, and I'm adding, looks like the get method, And at this stage now, I have to tell it, well, what lambda should it forward a GET request to the to-dos path? What lambda should it forward those requests onto? And what type of integration should it use? So here I'm creating an instance of lambda integration. That's essentially my lambda proxy type integration. This is just the class name that the CDK has for it. This here is just a reference to my lambda function, which I've just defined up here on the top. As I said, we're not interested in looking at the internals of that. And okay, looks like we need to set this proxy property to true, which probably suggests that there are alternatives, but I haven't looked at the alternatives. So the net effect of that code, the net effect of this code has just been to add on the get endpoint to /todos. I do a similar thing for post. And here what I'm doing is I am adding another resource stroke endpoint, but I'm not adding it to root. I'm actually adding it to the endpoint that I've already defined up here. See, this here is referring to this guy. So essentially, I'm tagging on this endpoint here. I'm tagging it on to the earlier endpoint. And the path name, in this case, the path name contains curly braces around it, which really means that this thing here is a parameter. It's a path parameter. So it's going to allow me to have /todos/1234, where 1234 is the to-do ID, which clearly my lambda needs to be able to pick up, and I'll talk about that in a minute. The rest in is as before. What type of method? Is it a get, put, post, or delete? Get in this case. And I've just been lazy. I'm actually forwarding everything onto the same lambda, but that's okay for now. We're not doing any processing in the lambda. Don't worry about this line at the end. You don't need that. So that's the CDK code for creating an API gateway instance and then defining the various endpoints or resources associated with the RESTful API that's associated with that gateway. And what I want to get across is, so even though I'm not showing you the lambda or lambdas, which would be in real life, the various lambdas behind these endpoints, but what I am showing you here is so we know that the lambdas takes two arguments, and the first one is the only one that we're interested in. The event argument is the first one that a lambda expects. So what is the structure of the event object that's passed on by API gateway, passed on to our lambda instance? And although I'm not showing you the full structure because it's just too long really to show on one screenshot, what I am trying to get across here is, let's supposing there was a query string part that could be added on to a particular endpoint. How is that query string accessed by my lambda? And the answer is, well, it's contained within the event object, but the API gateway will take care of putting it into the event object, because it's the API gateway that's actually going to create, it's going to be invoking, essentially, it's going to be invoking your lambda, and it's going to be passing the event object onto it. And I talked about the fact that API gateway for this particular type of integration, it takes the HTTP request and it creates a JSON object representation of that request. Well, that JSON object is my event object. And inside in that event object, it will have obviously the body accompanying the HTTP request, if there was a body, but it would also put all of the headers that might have accompanied the HTTP request. It will put any query string part into that JSON object. And so here I'm showing you down here, I'm showing you, it's a screenshot from CloudWatch logs, because what I did in my Lambda function was the very first line, I just did a console log of the event object. And that's what I'm looking at here. But I've actually opened up the full structure of that event object, and I've essentially kind of scrolled down, and we can see that this part here is the part of the event object that contains the query string parameters that were part of the original request. And so the API gateway takes care of creating this little substructure within the event object for me. So it's nice and convenient for my Lambda now to pick up the query string key value pairs and do whatever it wants to do with them. So that's how a query string can be accessed by your Lambda. In terms of path parameters, so one of the paths, one of the endpoints that I had in my CDK code there was /todos/ a to-do ID. So this 1, 2, 3, 4 is what we would call a path parameter in the language of REST, I guess. Equally, the question is, how does my Lambda get at that? Because presumably it needs to get at it to maybe do a read from the DynamoDB table. Well, it's the same answer as the previous screen, really. The event object will contain any path parameters that are appropriate. And again, API Gateway takes care of that for us. And so here's the same kind of screenshot. And I've opened up in CloudWatch logs the structure of the event object that was passed into my Lambda. And here we have, within that event object, we have a path parameter part. And if there weren't any path parameters, this key is still going to be in the event object, but the value is going to be undefined, obviously. And to go back to the previous screen, if there was no query string, there would still be a query string property or key in the event object, but the value would be undefined. And so you have to be conscious of that it's possible that the query string hasn't been set up properly or hasn't got any values. You kind of have to build that into your Lambda function, I guess. Just check to see if the query string part of the event object is undefined. If it is, and it should have something in there, then return a 500 error or throw a return a 500 response back to the client, whatever. Right. So in next week's lab, you create a RESTful API for, I think we had, I stuck with this movies context, which is something that we were familiar with from last year. Now I've actually, in my VS Code, okay, in my VS Code, this is essentially the end result of what you will be doing in next week's lab. So we've got these get movies. If I look at the stack first, I guess. I've got a movies table. That's okay. The partition key, which is also the primary key, is just the movie ID. That's fine. Nothing else there. I've also got a movie cast table. So the idea of this table is that it stores information on the cast members for a movie. And so each item in this table you'll have one item per cast member for a movie. So clearly movie ID now is not going to be sufficient to uniquely identify each item in this table, because a movie is going to have more than one cast member. So I've just, again, arbitrarily decided that even though it's calling it partition, oh yeah, sorry, my partition key is still going to be movie ID, but I've got a sort key in this case. And I've just decided that it's, I'm going to use actors' names rather. Okay, I could have used actors' IDs, but just for the sake of variety, it's actors' names. It's going to be my sort key. So they're going to be strings. Yeah, they're going to be strings. The sort key is going to be a string type. This is just the, what's here, movie table. Oh, I've actually created a local secondary index for my movie cast table, where the alternative index is going to use the role name as the sort key. So whereas the primary index has the actor's name as the sort key, the alternative index has the name of the character that the actor is playing. That's actually the sort key. So this is going to allow me to send requests like, give me the record or records items, sorry, give me the items from the movie cast table for movie 1, 2, 3, 4, where the cast, where the character's name or the role name was Joe Bloggs or just Joe, in which case it would give me all cast members whose name began with Joe, let's say. That kind of idea. Okay, so that's the local secondary index. These are some lambdas, various lambdas, more lambdas. Eventually we'll get to the API gateway part. That's just the seeding stuff. And here we go with the API gateway stuff that I was just talking my way through there, with various endpoints and all of that. So that's fine. So I've deployed it already. So if I go to API gateway, and there it is there. And if I go into it, and then both of these are actually quite good. Stages is good as well. If we click on, we'll stay with resources. That's the one I showed you on the screenshot. And so here we can see the full set of endpoints. In terms of the lambdas behind the scenes, even though we don't need to look at the code, you can study that yourselves. Although I might say a little bit about it in a second. But if I go to the Lambda service, and if I pick, let's say, this one here. So this Lambda, I know from the name of it, this Lambda is reading all, it's reading all the movie records, actually, it turns out. Let's just pick this one. It doesn't really matter. It reads a particular movie record, I think. So I was talking to you last week, was it last week or maybe the week before, when I was talking about lambdas and about the permissions side of a lambda, which we, from a management console perspective, we can see here. And I said that a lambda has, you have to define both an execution role and a role-based policy, or a resource-based policy, sorry, for a lambda. The execution role, if you remember, the execution role determines what other services my lambda can interact with. Now, this particular lambda, even though I haven't shown you the code, it's doing console logs and it's talking to my DynamoDB database. So it needs to have the appropriate IAM policies to achieve that. I also said that it's good practice, and the CDK follows this, it's good practice to define a role specifically for a Lambda function rather than sharing an IAM role across multiple Lambdas. That's not considered a good idea. So and the CDK takes care of that for me. So it has defined this role. And if I drill down into it, I would see that there would be policies associated, IAM policies associated with this role, which would allow it to use the CloudWatch logs service and to create CloudWatch streams and groups and write to CloudWatch streams. There would also be a policy that would allow it to, I think in this case, just read from the DynamoDB service, and in particular, read from my table within the DynamoDB service. Visually, we kind of see here what the execution role is permitted to do, because it looks, if I select this drop-down menu, it's showing me, well, this particular Lambda has got some IAM permissions related to CloudWatch and related to DynamoDB, and that's consistent. And if I do, just in this case, because I think I kind of slightly stumbled through the last day, but if I click this role, now, in truth, you shouldn't, rather than you shouldn't need to go drilling into this aspect of a Lambda unless there's something that is some permission that you want to assign to a Lambda that's slightly non-standard. And certainly Lambda talking to DynamoDB, that would be pretty mainstream, which is why the CDK takes care of all of that for us, really. But if you wanted your Lambda to talk to some other service that's not that commonly used, then you would have to write an IAM policy within your CDK and attach that policy to the Lambda's execution role. You actually have to program that at the CDK level. Now, I haven't shown you anything like that so far. I may show you an example of it a little bit further down the line. But to stick with this particular Lambda, which we know talks to CloudWatch, and here we're looking at the role, and here we're seeing what permissions. And so we can see, look, there are two policies attached to this role. And again, this one looks like, well, both of these policies are what are called managed policies. They're predefined policies provided by IAM, really, and CDK leverages them, because again, what this Lambda is doing is pretty mainstream, as I said. But so this one, I happen to know this policy is the one that allows the user of the policy, my Lambda in this case, to talk to CloudWatch logs. And can I prove that, I wonder? If I click on the policy, and do I have the JSON? It's a rule, actually, isn't it? Yeah, let's see. I wonder where does this one take me if I click through on that. Oh yeah, let's see. Am I getting any closer? You can see here, and from the names, look, it's allowing creating log groups, creating log streams, writing to log streams. I mean, if we click down through these, we will actually eventually, I guess, see the, actually, let's select JSON. That's a better representation. So this is the JSON representation of this particular policy. And I'm assuming now you've seen, or maybe in outline form, the structure of these IAM policies in JSON representation from last year. And so what this policy is telling us is that it's telling us what the service or the resource, sorry, that's associated with this policy. They're allowed to use the CloudWatch log service, and in particular, they can invoke this method of that service as well as this method and so on. So that's kind of proving now that if we work all the way back, this policy is attached to the role associated with my Lambda function, which is what allows the Lambda function to do console logs, essentially. If I detached this policy from the role, then my console logs would actually throw an exception coming from IAM, really, because it's the one that validates all of this stuff. And similarly for the DynamoDB one, how many windows have I got open now? If I go back to is DynamoDB here? Oh yeah, here's the DynamoDB policy. And if I keep drilling down through it, here's the actual JSON representation of that policy. And in a similar vein, this is telling me that here are the actions. Does it say allow or deny? Should say somewhere. So these are the actions that are allowed. And again, in this case, the service is DynamoDB. And here are the actions that the holder of this policy is allowed to do. And all of the actions, if you kind of scan down through them, they're all kind of read related actions. There's no write related action here, which means that the Lambda function that has this policy attached to it or associated with it, it can do read operations, but it can't do write operations. That's the way I've just, in my CDK, I mean, this policy here that I'm showing you here now, this was all attached to the permissions of this Lambda function as a result of, if I go back to my CDK code, as a result of, let's see, this line of code, okay? This line of code, I'm saying, okay, now you haven't seen this code now, but movie table, that refers to the table that contains all my movies that I mentioned. The movie table is granting read data permissions to this Lambda function. And the variable that I've highlighted there, if you scroll back up, that's the reference to the Lambda function that I've just been showing you on the management console. So one line of code in CDK essentially did all of the work behind the scenes that I showed you there through the management console. Okay. Oh yeah, there's one other thing that I want to mention in relation to Lambdas and permissions. So I'm not sure how many windows I've got open now, but okay, so here I am back at the Lambda service, and I'm looking at this particular Lambda function. And I've just been talking about the execution roles, which again is that part of a Lambda's permission that dictate what other services a Lambda can interact with. The other side, though, is what other services can invoke this Lambda. And that's controlled by what we called the resource-based policy associated with the Lambda. So the resource-based policy will control who can invoke this particular Lambda. And equally, the CDK has taken care of this for me, and it's taken care of it for me because if I go back to my CDK code, and we're sticking with this get movies by ID. That's the particular Lambda that we're looking at. And if I look at my API gateway configuration, somewhere in here, there is going to be a reference to that function. Let's see, can I find it? Here we go. There it is there. Because I'm associating this function, this Lambda function, with a Lambda integration for my API gateway, that means that the resource-based policy for this Lambda function must allow API gateway to invoke the Lambda. And that would be determined by the resource-based policy associated with the Lambda. But because of the code that I'm just highlighting here now, because of this code in my CDK script, behind the scenes, what has happened is in the resource-based policy for this Lambda, we can see if I click on any one of these, I think I'm not sure why there's two, but if we clicked on one of these, so this, I'm going to click on the resource-based policy for this Lambda. And if you can kind of see, it relates to the principle here is API gateway. And the API gateway, it looks like it's allowed to essentially, it's allowed to use the Lambda service. It's allowed to execute the invoke function of the Lambda service. And the condition here essentially says, kind of in plain English, what the condition says is it can invoke Lambdas that are essentially associated with my AWS account in the EU West 1 region. It doesn't be any more, it's not any more specific than that, it looks like. It's not specifying a specific Lambda instance, I don't think anyway. But because of the presence of this policy in the resource-based policy of the Lambda, that's what allows the API gateway to actually forward HTTP requests onto my Lambda function. Right. So there's a lot of stuff going on down below the surface, if you like. That's API gateway. So we've only looked at the creation of RESTful APIs and looked at the AWS proxy stroke Lambda proxy integration aspects of it. Lots more that we haven't gone near. The next and final serverless service that I want to look at is Amazon Cognito. And I'll just do a little bit on this, if that's okay. So back to this diagram that I had a couple of slides back. And now I've actually I've slipped in this Cognito service as being part of kind of state management side of a serverless app. And in particular, it's the user accounts state management part that Cognito is concerned with. So we don't have to have our user accounts kind of stored inside in some sort of DynamoDB table. Cognito can do all of that for us. Cognito is a little bit clumsy to work with, to be honest, but the service is there for a reason, so we will get to use it, or we may as well use it. So what is Amazon Cognito or AWS Cognito? It essentially allows us to give identities to the users of our web API. It doesn't have to be associated with web APIs. It could be more general than that, although that's the content in context in which we will use Cognito. But in very high general terms, it's a service that allows us to give users identities so that those users can use our apps, whether the apps be a web API or some other form of application. It could be an application running on an EC2 instance. It doesn't really matter. Now, Cognito has two types of resources, let's say. It has what are called user pools, and it has identity pools. And anybody coming to this stuff from the outset, they're a tiny bit confusing. We will only look at the user pools side of it. And the user pools resource is really aimed at this, your kind of standard signing in functionality. If you've got the need for a sign-in functionality for some application that you are hosting on AWS, in fact, it doesn't have to be running on AWS, but you want some sort of sign-in registration functionality, the Cognito user pool resource is what you want to create for yourself. And it does indeed integrate well with API Gateway, but it integrates with other services as well. The identity pool it serves a similar purpose. Its purpose is to allow users to use particular services that you want to make available to them. But whereas with the user pools, it works with your kind of standard username, password type set of credentials. With identity pools, what an identity pool will give a user is a set of AWS credentials. And it will have a timestamp on those credentials. So that's like the same kind of credentials that you would have created when you created the IAM user at the start of this module and you downloaded a set of access keys. Well, identity pools essentially generate a set of access keys, public and secret access keys for users, and hence allows them to access particular services within your account, if you like. And you can actually integrate user identity pools with user pools. So you might have a scenario where you've got an application, let's say, let's stick with the API gateway. You've got an API, a RESTful web API, and you want to allow users to use it. So you create a user pool, and users get their username and password. They choose them themselves, really. And so they kind of sign in the normal kind of way. But maybe that application, let's say it has an S3 bucket that you actually want to allow users to upload directly to the S3 bucket. Now, the user pool won't really serve that use case. Instead, what you want to do is to give a set of access keys, albeit temporary access keys, to a user to allow them to kind of physically upload an object into an S3 bucket. And that's where the identity pool would come into play. It would actually be responsible for generating those temporary credentials. But the identity pool record, if you like, of a user can be linked to their user pool record. It does get a little bit cluttered and slightly confusing, admittedly, but we won't be looking at identity pools anyway. They're also called federated identity pools, just to complicate it even more. This is a very kind of broad statement, but if you're talking about you've got a large number of users and you want to give them access to applications, then user pools is the route to go. If you've got a small number of users and you want to give them access to, be it applications or services, then Cognito identity pools might be the way to go. The identity pools are more kind of fine-grained in terms of what kind of access you're giving to your users. So we're focusing in on the user pool side, and so what a Cognito user pool allows you to do is it allows you to create, yet again, it's essentially it's a serverless database. That's really all that's going on behind the scenes. But you don't operate at the kind of database level. But it is a database of your users for your both web and mobile apps. That tends to be where user pools kind of shine. If you want to allow users, give them authorization to use web apps or mobile apps that you have hosted on your AWS platform. It's your standard kind of simple login, username, password, username or email password kind of combination set of credentials. And the user pool resource can handle all of this stuff as well. It can handle password resets, email and phone number verification. So like we've all registered for some online service, and part of the registration process is that the service, let's say it sends us an email when we register with some sort of verification code, and then we've got to input that verification code on a screen, and that confirms our registration. Well, all of that logic, if you like, behind the scenes, user pools can facilitate all of that, and we will get to do that actually in the lab next, maybe not next week's lab, certainly the week after. You can have multi-factor authentication. You can enable that at the user pool level. You can have federated identity, so maybe rather than requiring users to create a special username and password for a particular application, they can use their social media as a way of logging into your applications. What else am I mentioning? You can selectively block users' accounts, maybe because their credentials have been exposed. So that's quite an easy thing to do. You would tend to go in at the management console level to disable or temporarily disable a particular user's account. Login sends back. Oh yeah, we're back to, so when users log into our application via Cognito, Cognito uses JSON Web Tokens, which you're familiar with from last year. It uses those as a way of authorizing users to use particular parts of your application. And we will see that at play in next week's lab. So it has all of that kind of standard authentication and authorization built into it, so that we don't have to program it all ourselves. You might remember last year, you had to program all of that, which was great. You have an understanding of it at a lower level. We can kind of elevate our code base up to a slightly higher level and let Cognito take care of some of the messy stuff that goes on behind the scenes. In very general terms, this is kind of what happens behind the scenes. So your client, first of all, assuming now you've registered with Cognito, when you want to try and access a particular application in terms of kind of logging in, you authenticate with Cognito, giving it your username and password. It sends back a token. We know now it's a JWT token, although it probably supports other types of tokens. And then that token is used with the various requests that you send to your API gateway. And API gateway extracts the token, but API gateway doesn't take care of verifying that the token is genuine. It will actually ask Cognito to do that for us. So as I mentioned in one of the earlier slides, these two services dovetail very nicely with each other for obvious reasons. And then what Cognito will do is, if it's happy that the token is genuine, then it will essentially allow it will allow the gateway to forward the request on. And it does that by means of an IAM policy, as we'll see. This is a more detailed and a more accurate representation of what's actually going on in the previous screen, though. So in real life, what we tend to do, we don't have to, but what we tend to do is we tend to have two API gateway instances. One of the gateways just deals with authentication related requests, including registration and login. The other API gateway is the one that contains or that deals with accepting requests for triggering particular piece of functionality in your application. Okay. And so you can follow the numbering sequence. So for your typical user, first of all, they will send a request to this gateway, and that would be your typical kind of login request. So maybe they're filling out a form. We don't care about the front end now really, but they're filling out a standard login form. Those credentials are sent to this gateway, and this gateway via a Lambda, which we have to write. This Lambda takes care of interacting with Cognito. So whereas in the previous screen, if I go back to it, in the previous screen, it's kind of suggesting that these two services are talking directly to each other. They're not really. There has to be a Lambda in between, which we have to author, although there are kind of templates. And that Lambda is the one that takes care of the communication that's going on here. So following our step one, so username and password, let's say, those credentials have been entered. It's passed on to the Lambda. The Lambda talks to Cognito, and it would have to tell Cognito the particular identifier of the user pool that Cognito should look up to see whether those credentials combination are valid or not. Let's suppose assuming they are, comes back with a positive response, and it will come back with a JWT token, which is forwarded back to the gateway and back to your end user. Your end user then tries to access a particular piece of your application's functionality. So this request goes to the second gateway. The request includes the token, and we need a Lambda function which is going to play the role of what's called the authorizer. It is the one that checks that the token is a valid token. It will communicate, although I don't have it here. It may communicate with Cognito to achieve that, but again, we actually have to write a Lambda to carry out this authorization step. There's lots of them online, really, so they're fairly standard coding. And it is this Lambda, it is the one that generates on the fly an IAM policy that either instructs the gateway to deny it access to the whatever's on the right here, which in our case will be a Lambda, or allow it to forward the request onto the Lambda. So from our point of view, we've got to, number one, create the Cognito user pool. We've got to create two API gateways, configure them with the appropriate endpoints, and write these two Lambdas. That all is stuff that we have to put together. Now, it certainly is. It's too late to get stuck into all of this stuff now because it's quite heavy going, but we'll look at it next week, which probably means we won't get to practice it until the following week, which is after the midterm break. But that's okay. That's kind of how I had seen it rolling out, if you like. So I'm going to pause it there for today. And again, as usual, I will, it's at the end. I'll allow any questions if you've got any questions, whether it be in relation to what I've just been talking about or labs or anything else. The other, I don't know, is it good news or bad news, is I'm putting together the specification for the first assignment, which is going to be worth 40%. And the first assignment will be to develop a RESTful web API and as well bring in Cognito into the whole equation. But really, when we do the Cognito lab, that's only when this stuff is going to make hopefully make more sense to you as to how it all hangs together and how the various mechanics of it work. So I'll talk about the assignment specification to you next week. Okay, doesn't sound like anybody has any questions, so we'll leave it at that, and I will talk to you in the labs next week. Thanks.